Okay, so in algebra we had what was called sigma notation. We would take a symbol, the sigma notation has this sigma symbol, and you would have a k value, and you would go up to n. And then you have an equation written in front of your sigma. So if you had a of k going from k to n, then what this actually means is that you would take a of 1, so you want k starting at 1, and the sigma means to add each of those values. So you'd have a of 1 plus a of 2 plus a of 3, and you would continue on until you got to a of n. So this is what we call sigma notation. Okay, now we can make that, we have what's called a Riemann sum. So when we looked at the areas of the rectangles added up together, we can notate that by using Riemann sums. And that Riemann sum would be the sigma notation, where k starts at 1 and then goes through to n. And we would have the height of the triangle. You would plug the value into your function and multiply it by the width of x, or the change in x of that k value. And that was giving us the area of each of those rectangles. So this is the height of the rectangle and the width of the rectangle. And we would find them and add them together, just like we did last time. So if we take now these Riemann sums I talked about at the end of the last lesson, that the smaller those intervals get, the better the approximation becomes. So when we look at it as a limit, and we look at the limit of this Riemann sum, it would get closer and closer to the actual area under the curve. So the limit of the Riemann sum as the width gets closer to 0. So as the width approaches 0, that is what is the integral. So we will call it an integral. And what was the integral? What did it actually represent? It represents the area under the curve within the limits that are given. So it actually is the area under the curve, just like we calculated with those rectangles. So we have the limit of the Riemann sum as the width approaches 0. Okay, so this is similar to what we did with derivatives. So now with the integral, it works the same way. We want to make it so that that width is closer and closer to 0 as we're approximating, and it gives us a more accurate and much closer approximation to what the area is. So if we look at, what we're going to look at first, before we kind of calculate those, is where the notation came from and switching between that sigma notation into what we will now have as our integral. So we have, first of all, we have Leibniz, who we first have the Greek numbers and letters, and we're going to switch it because we have to get into the Roman letters, which is what Leibniz used for his integrals. So the Greek lettering was that we would find, like if we wanted to find an integral, it would be the limit as the change in x approaches 0 of the change in y over the change in x. Okay, so this is the derivative here, right? Because we have the limit as x approaches 0 of the change in those, which is our slopes. And when we switched it, so this is from Greek into the Roman symbols. When we switched that for our derivative, it became dy dx. Okay, now the same thing, let's look at the Greek for our derivative, or for our integral going into the Roman. Okay, so the Greek notation would be the limit as n approaches infinity. Because remember now, n is each of those intervals that it's going through. So we have as n approaches infinity of the sigma notation from k equals 1 to n of f of c of k times the change in x. Okay, so now what happened when it became a Greek interval, we had to, at this point, you still had to tell what your starting and ending point are also. So our new notation also gives us a little bit more information within the equation. So it becomes what we've seen, I think you've seen before possibly, is that elongated s. That gives us, that means an integral, and we're going to go from a to b, and we would take the function f of x, and the change in x becomes what would be our dx, which looks very similar to our derivative also. So we can start connecting some of these things. So this is what's called an integral. Okay, so let's look at it one more time. We have an integral. Okay, so we have, so you're going to have that, it's kind of a longer s. And this is just means integral. So this makes you know that what your process you're doing. So this is the integral sign. A and B. A is your lower limit. B is your upper limit. And then the function that you have inside of there is what is called your integrand. And d of x tells you your variable of integration. Okay. Now in derivatives, you have to know what variable you are taking the derivative with respect to. The same as when we did the implicit differentiation. You have to make sure you know which variable you are deriving with respect to. The same as when you're taking the integral. You have to know which variable you're taking the integral. So when you're taking the derivative, when it says dy dx, then you would take with respect to x of the function y. On the integral, the same thing. Whatever is here after, if this says dt, then you would take the integral with respect to t. So it tells you what to do on that as far as when you're integrating it there. Okay, so let's talk a little bit about, so we know that the integral gives us the area underneath the curve. And so we're going to take, and just make sure you know how to express your integral from a Riemann sum into an integral, because that's what you're going to be asked to do. So you're going to take something, so let's take an example here. If I tell you that the limit as n approaches infinity of the sum from k equals 1 to n of 3 times the midpoint k squared minus 2 times the midpoint at k plus 5 times the change in x, and I want to know on the interval from negative 1, from negative 1 to 3. And I want to know what is the area from that in that range underneath the curve. So I want it to be written in the Roman symbols instead of the Greek symbols. So what do each of these things mean? So first of all, like I said, the integral, it includes more information because this right here, the interval of how far you're going, is included in the integral notation. So we start with an integral, and what are the limits? Where are we going? From which point to which point? And it's important to know that the smaller point is usually on the bottom, mostly for this introduction to integrals. So on here, we want to go from negative 1 to 3. So we would start at the bottom, negative 1 to 3. And then we want to know what is the function. Well, this here is the function, but we've been plugging in midpoints at those values. But when we're using an integral, we don't need to do that because our midpoints now, because we're making those, the width of each of those rectangles as close as 0 as possible because we're taking the limit, then now we can just plug in those values of x. So we're going to take, so this becomes 3 times x squared, because we don't need the midpoint anymore because we're so close together, minus 2x plus 5. And we want to know which variable we are taking the integral with respect to. So here it tells us the change in x, so we would write dx at the end. So now we know we're taking the integral of 3x squared minus 2x plus 5 with respect to x. Okay, so we're gonna I just want to make sure that we're thinking about this as an area. So we have, we looked at before those curves, but I want a little definition here. What is the area under a curve? Okay, so we have the area under the curve. So I'm going to read the math language to you, and then we're going to just write down the definition in the math language. So if y equals f of x is non-negative, so it has to be positive, and is integrable over the closed interval from a to b, then the area under y equals f of x from a to b is the integral of f from a to b. So all of that is saying is that we are looking at if it's, as long as those values are positive. So y equals f of x has to be positive. We're going to look at what happens as it's negative. But when it's positive, then we can just take the integral from a to b of that equation, and it'll tell us the area under the curve from a to b. So for instance, if we have to have a positive graph. So let's just look at our x squared graph on this side here. Then we would have, if I want to know from a to b what the area is under the curve, then to find that, I would take the integral from a to b, where this function is f of x, of f of x dx. Okay, so it's much more compact than using this sum notation there. So you can use, so we're not going to actually figure out this lesson how to find the integral, but we're going to use areas to find what the integral equals. So we're going to do the reverse. So let's look at an example. If I want to find and evaluate using the graph of, let's see, I want to find this integral from -2 to 2 of the square root of 4 minus x squared dx. Okay, now we haven't learned how to do this yet, but what does this graph look like? This graph is half of a circle. It is the top half of the circle. And so we're going to take it, it's a semicircle, and it has a radius of 2. Okay, so if we actually worked this backwards, it would be x squared plus y squared equals 4. So for instance, we have the square root of 4 minus x squared equals y. So if we square both sides, we get y squared equals 4 minus x squared. Add the x squared to both sides, we get x squared plus y squared equals 4. And the area, the equation of a circle tells us that this is r squared. So we know that it's a circle that has a radius of 2. So on here, and because we only have the positive square root, it's only the top half. So what we're actually looking at is this. And it's asking us from -2 to 2, what is the area? Well, right there, we don't know how to calculate that yet, but we do know how to calculate the area of a semicircle. So if the area of a circle equals pi r squared, then what is half of the area? Or the semicircle. So half the area of a circle, or the semicircle area, which is the same thing, then would just equal 1/2 of pi r squared. Okay, so we have here, we know that the area equals 1/2 pi r squared, where r is equal to 2, the radius of the circle, squared. Okay, so when you multiply these two together, well, first we get 1/2. This 2 squared becomes 4, so we have 4 over 1 times pi over 1. So we can cancel out this, reduce it, so we get 2 pi. So now we know that the area of this semicircle is 2 pi, which means that the integral from a to b of the square root of 4 minus x squared dx equals 2 pi. So as we calculate those, it just helps you to connect what we're actually doing, and that we are taking the area under the circle is the same thing that we're evaluating. Okay? Okay, so we have, so what happens if the area is negative? You'll get negative areas also if it's below or above. So we said it had to be a positive equation. If it does go below and there's some negative part of the equation, then you have negative areas too. So for instance, an example of this would be if we're taking a sine curve. So if I want the integral from 0 to 2 pi of sine of x dx. Okay, well, we want to know what that area is. Well, if you graph it based on its graph, because we haven't learned how yet, so we're just doing by graphs still, then we know that the area, to find it, we would draw out what our picture looks like. We go from -1 to 1. The sine curve starts at 0, 0, and then halfway, and then a full sine curve is in 2 pi. And so this halfway point would be our pi. So we start here, go up to 1, come back down. This will go all the way down to -1, and we come back. Well, what happens is that we're looking for the area that's between under the curve. Well, that's if it's positive. Actually what we're looking at is the area between the curve and the x-axis. So this becomes an area and this becomes an area, but this area is under the x-axis, so it's a negative area. So when you look at this, we have the same size here above the x-axis as we do below the x-axis. So if you add those areas together, anything subtracted by itself is 0. So we find that the integral from 0 to 2 pi of sine x dx equals 0. Okay, let's look at another example. What is the integral from 0 to b? So what if we don't give a set of value of 4x dx? Okay, now we're going to put a qualifier in here that b does have to be greater than 0. So what are we actually looking at? So we're going to take and graph the equation that we're given, and then we're going to find the area under the curve. So the equation that we're given is 4x. Okay, 4x has a y-intercept of 0 and a slope of 4. So we'll go up 4 and over 1. So if we want to know the area under that curve from 0 to b, wherever b is, then we are calculating, what we're actually finding is the area of a triangle. You see how that's a triangle there? So what's the area of a triangle? The area is 1/2 base times height. Okay, so you do need to know some equations from other sections here. So if the area is 1/2 base times height, then we know that the base is going to be whatever this width is here, and the height is going to be pretty much whatever this y value is when we plug it in here, right? So if we wanted to find, for instance, if I want to know at 2 how tall this graph is, where it's at, then I would plug in x equals 2 in here, and it would be at 8. Okay, so we know the area equals, so I'll put it in right here, 1/2. The base is just going to be whatever this width b is, which we don't know. We just called it b. So we're going to keep it b times the height. Well, the height will be calculated by plugging b into my equation. So the height will be 4b. Okay, so if we're looking for the integral from 0 to b of 4x dx.